Okay, let's get started. In this lecture, we're going to cover speculation, and our focus will be especially speculation in parallel machines. Parallel machines meaning multi-core, multi-processor, or multi-threaded machines. This is another fascinating topic that has fascinated many people in the world, and many researchers have done a lot of research on this. And in fact, my PhD thesis was on a topic called run-ahead execution, which is essentially speculation, except it was not on a parallel machine, although it could be adopted to a parallel machine, and other people later adopted to it in a parallel machine, as we will discuss with the concept of dual core execution. But basically, that's the idea that we're going to focus on today, speculation. Oh, looks like we're having trouble. Speculation, basically these are some of the readings that are required. Soy et al., Multiscalar Processors, a seminal paper on speculation. We will cover that. Zhao's dual core execution work, we will cover that again. Later on, there are two aspects of speculation. Speculation to improve single-threaded programs and speculation to improve parallel programs. The first two papers cover the aspect of speculation to improve single-threaded programs. How can we basically use speculation to parallelize a single-threaded program? The second two papers cover aspects of using speculation to actually improve the parallel performance, parallel application performance. One is transactional memory, which is actually used in some systems today. And the other is speculative lock elision, basically transactional memory done underneath without support from the programmer, at least without much support from the programmer. And there are a bunch of recommended readings that I have. One is actually Stefan, that should be Stefan et al., A Scalable Approach to Thread Level Speculation, one of the earlier thread level speculation papers. The other one is Dynamic Multi-Threading Processor, Hytham Akre and Driscoll's paper. And there are many, many others that I will talk about during this lecture that I hope you will read about. So the focus of this lecture is speculation in parallel machines. What is speculation? Speculation is doing something before you know it's needed. This is the most general form of speculation. Basically, before you need something, do it. For example, before you know that you're going to fetch this instruction, fetch it. And you need that to keep the pipeline full, right, in a single-threaded machine. So this is mainly used to enhance performance. In the single processor context, you know of many techniques, and we've studied many techniques previously, especially if you have taken my class 447, Computer Architecture, whose lectures are available online. You can actually go back and look at branch prediction, for example. Branch prediction is a form of speculation in the context of single processor. You fetch the next instruction before you know that you should fetch that instruction, right? That's the idea of branch prediction, to be able to keep the pipeline full. Data value prediction is another concept. When you load a data value, maybe it takes a while to load the data value. Why don't you predict that value so that you can speculatively process the dependent instructions? And this breaks the data dependencies between instructions and enables instruction level parallelism. Of course, you will need to verify the speculation that you did in branch prediction and data value prediction, right? If you mispredicted the branch, when the branch actually resolves, you need to recover from that misprediction, so that by redirecting the fetch to the correct destination or correct target of the branch. Similarly with data value prediction, if you mispredict the data value, all of the dependent instructions may be executed, and you will need to recover from that by actually either re-executing the dependent instructions or flushing the pipeline and restarting, just like you would normally do with a branch prediction. Prefetching is another form of speculation. Basically, the processor requests an address before it knows it really needs that address, right? It could figure out based on the address patterns that are happening so far. For example, if the program is generating addresses that are predictable, then the processor itself can start latching onto that address pattern, the prefetcher. Let's say the program has generated A plus 1, A plus 2 to memory to access. Prefetcher can start saying, oh, I expect the program will continue accessing in this streaming fashion or striding fashion with a stride of 1 cache block. And the prefetcher can start prefetching these blocks, right? And this is a form of speculation because the prefetcher just guesses that the processor will continue accessing memory in the streaming fashion, right? Well, in this case, you don't need to recover from it potentially, right? Because there's no harm done. This is purely speculative. whereas branch prediction normally is not purely, it's a speculation mechanism, but it does affect correctness if you do not correct the outcome of the branch. Okay, so these are some of the techniques we had considered when we covered speculation in single processor context. Today, our context will really be parallel machines or multiprocessors. Basically, what are the speculation techniques to improve performance on a multiprocessor system? If you would like to learn more about the single processor context, I would encourage you to go and watch the branch prediction lecture from 447. I believe it's lecture 10 or 11, and it's on YouTube. And data value prediction and prefetching are also covered in lectures in 447, and you can find those lectures on YouTube as well. Or I'd be happy to discuss that in a recitation. So let's take a look at the multiprocessor context. Multiprocessor context, again, there are many speculation approaches. Thread level speculation, transactional memory, and helper threads, but we're going to examine many others. So basically, the idea is to speculatively parallelize the programs in a multiprocessor to improve performance. To be able to do that, we would like to execute threads unsafely in parallel. Unsafely meaning we do not know whether or not we should be executing threads in parallel. Right? That's the idea. Threads can be from a sequential or a parallel application. This is the most general form of speculative parallelization. We want to parallelize either a single thread application, or we want to expose more parallelism from a more parallel application. Well, once you start executing threads in parallel without knowing that they can be executed in parallel, they might actually have data dependencies, right? You need to somehow check for these data dependencies. Let's say you've generated this thread 0, this is a thread that's executing, and you start to speculatively fork thread 1, and you continue executing thread 0. And you do not know whether this thread 1 has a data dependency with thread 0, right? Before you start executing it. But somehow, this thread 1 may write to a location that's later read by this thread 0, which means that they shouldn't be executed in parallel, at least purely. So hardware or software monitors for these data dependence violations, and once it detects that, if there's an ordering, data dependence ordering is violated, then the offending thread is squashed and restarted, right? For example, this thread, this is one form of data dependence speculation, that violation. It may be that this thread does a load, and this thread may be logically earlier in the program, and this thread should have done a store, and this thread did the load earlier, but this thread does the store later. This thread got the wrong data value because it did the load much earlier because it was executed in parallel. If it were not executed in parallel, this load would have been done later than the store. And the hardware or the software somehow detects this, and it detects this data dependence ordering violation. This load must have been done before the store, but because of speculative parallelization of these two threads, this store happens later than this load. As a result, there is an offending thread. Offending thread is thread 1 in this case because it's logically later. It should be logically later, but it got the data value that's stale, that was not updated because it executed too early. So this thread can be squashed and restarted. This is one way of actually monitoring and recovering from data dependence violations. Why? Because this thread's execution was unsafe, right? We started executing this thread earlier than we knew whether or not it had a dependence to this part of the program. Right? If there's no data dependence, if you actually spawn this thread and it turned out that these happen to be totally independent, then the thread commits. So one example over here is like basically, let's say you have a single-threaded program, you're executing it, and you have a function call, right? And you execute that function call. Normally, you would execute in a single processor context. But what you can do is you can actually launch another thread, thread 1, let's say, to execute this function call. It's on a separate processor, and this thread actually continues from the return of the function. And if this function is completely independent of this thread, and there is no data dependence violation detected, then you can commit the results of this thread. Somehow you need to merge the results into the architectural state, but actually you can commit, right? Because there is no dependence. So that speculative parallelization works in that case, right? If you're doing a function, for example, that's for cleanup tasks that the processor actually doesn't need over here with this thread, this could potentially happen. or if you're doing a function whose results will be needed much later in the program, you can execute that function in parallel early on right now with the code that's going on that's not dependent on the function, and then later this function's results will be available to other instructions that need the results, right? So this is one case where speculative parallelization can work, right? For example, if threads, if data dependencies are not violated, then the thread commits, the speculative thread commits. And if threads are from a sequential order originally, that sequential order needs to be preserved. If you're actually taking a single thread and parallelizing it speculatively, the sequential order needs to be preserved such that threads commit one by one in order. And we will see this. Basically, when threads execute speculatively, there needs to be inter-thread value communication, right? Let's say you've decided to launch a thread on a function call over here. Then these threads need to communicate somehow. And this can happen via register or memory. And let me talk about the different types of communication briefly, because this will come up over and over in different kinds of thread level speculation mechanisms. If the threads need to communicate through the registers, basically this needs hardware support between processors, right? Actually, the other one needs hardware support too, but the fundamental difference between register dependencies and memory is dependencies between threads are known by the compiler, right? The compiler, for example, when it's compiled the program, it knows, let's say you have a sequential program initially, and this chunk of the program is writing to register 2. And this chunk of the program, let's say this is a function call. You go to function call. This chunk of the program is reading from register 2, right? And doing something with it. Now, if you execute this function call separately as a separate thread, then this dependence needs to be satisfied, right? This R2 actually is executing on the separate thread over here now, because function is actually executing in parallel with whatever comes after the function, destination of the function, or return point of the function. And while that function is executing, this is reading R2, and this R2 is dependent on the other thread that was executing over here, right? So this can be detected by the compiler. That's the fundamental difference between registers and memory. Register dependencies can be analyzed and detected by the compiler because they're static, right? They're not dynamic. Of course, they're dynamic in the sense that they're dependent on the branches, right? That's one difficulty. But you know at least whether or not you may have a dependence or may not have a dependence. Only the branch determines that dependence. But register addresses are known statically, right? Dependencies are known statically. So this register communication, when it happens between threads, can be initiated by the producer of the register, which is this one, or the consumer of the register, depending on which one executes first, right? The compiler can say, oh, this is dependent. You need to wait for the value of the register. Sorry, I did this wrong. Basically, register 2 is used as a source over here. Basically, the compiler can say, oh, you need to wait for the value of this register. It's coming from somewhere. Or you need to send the data that value of this register because somebody else will need it. Compiler, after analyzing that code, that can put in these hints. And if the consumer executes first, let's say this is the consumer thread, thread 1, and let's call this thread 0. If this one executes first in parallel with the previous thread, let's say, and this might happen if you parallelize aggressively, then the consumer stalls. If the value is not ready in the register, it knows that it needs to wait, but the value is not ready in the register file. And the producer, when it executes, it forwards. So how do you know whether or not the value is ready? Well, basically, you can communicate with the register file, and register file can have ready bits, right? For each register in the register file, you can add a ready bit for that particular thread, right? In the hardware, and the ready bit is set if the value is available. And the ready bit is not set if the value is not available yet. For when this thread starts, if the value of R2 has not been produced, the ready bit for that R2 will be initialized to 0. And only when this producer executes, it can basically set that ready bit to 1. So these ready bits are also called full empty bits. And these are actually needed to do synchronization between threads at a very fine grain. Basically, whether or not the value of a register has been produced yet. And the producer sets the ready bit, consumer basically waits for the ready bit to become 1. This is basically data flow between threads. And full empty bits, one of the early introductions of this was Burton Smith's seminal paper on a pipeline shared resource MIMD computer. And I'd encourage you to read that. That has a good example of the use of full empty bits in the heterogeneous element processor that Burton Smith designed at the time. And this is ICPP 1978. But this is an important construct for communicating registers between threads. You could have full empty bits in memory also, actually. This is an important synchronization construct that enables one thread to produce a register or memory value and another thread to consume it. And this is how you can synchronize it. Basically, this is a synchronization variable. Ready bit is a synchronization variable that can be supported in hardware. And if you're doing thread level speculation, you should actually support this in hardware in registers, right? So you can read this paper for a good use of full empty bits. If the producer executes first, on the other hand, basically producer simply writes the result and sets the ready bit, and when the consumer actually executes, the consumer reads the value. And the producer can continue after setting the ready bit, of course. And we will see one example of this with the multiscalar processor. Multiscalar processor actually communicates between threads this way. There are full empty bits in the register file, and when a task, as they call it, produces a value that needs to go out to some other processor, and a compiler analyzes the task to know whether or not the value needs to go out to some other processor. Then the task, when it produces the value, it basically sends the value across the register file ring, and another processor that's needing that value captures it in its register file. But we will get to that. I'm getting ahead of myself. But this is another reading that you should definitely do. This is actually a required reading. Multiscalar processors in ISCA 1995 by Sohi et al. ISCA 1995. And this is one of your required readings. This is one of the seminal examples of thread level speculation done in hardware-software cooperative way. Okay, and they communicate registers values between processors this way. Okay, I've already said that this can be implemented with full empty bits in registers. Memory communication, on the other hand, is very different from register communication. The compiler has no idea usually about memory dependence. At least the difficult memory dependencies the compiler doesn't know. Why does the compiler not know? Because the compiler doesn't know the memory address of operations, and not everything is statically analyzable because of this, right? For example, if you use pointers in your program and dynamic memory allocation, you allocate memory to a pointer, and you allocate some other piece of memory to a pointer, and you can assign any value to a pointer, right? As a result, these dependencies are dependent on the dynamic inputs to the program, and how does the program behave based on those dynamic inputs, and the compiler cannot analyze that dynamic execution. As a result, memory communication is usually harder to satisfy between these different threads in speculative parallelization. But if you're speculatively parallelizing the program, you would like to know if there's a store here and if there's a load here, if this store and load actually overlap, right? Because if this load actually overlaps with this store, when you're executing this in parallel with this portion of the program, you would like to know that this load actually gets the correct value, and it actually doesn't get the stale value. And similarly, there may be stores here and loads here, and you need to know if this store A is overlapping with this load B, because it may be that you don't want the store A done before the load B if they're actually overlapping with each other, because this is from a logically later part of the program. Right? So you need to preserve the dependencies, obey the dependencies. In general, in thread level speculation approaches, a thread performs loads speculatively and gets the data from the closest predecessor thread. Right? And it keeps a record that it has read the data. And it keeps this record in the L1 cache or another structure. And we will see some examples of this. On the other hand, stores are also performed speculatively. When a thread does a store, it doesn't wait. When a thread does the load, it doesn't wait normally also, as I said earlier. basically, when a thread does a store, it may not be the oldest thread in the machine yet. So it buffers the updates while it's speculative, while it's not committed yet. Basically, it places the update in the write buffer or in the L1 cache. And when it does a store, it checks for successor threads for premature reads. So this implies an ordering between the threads, right? You have basically thread 0, thread 1, thread 2, thread 3, thread 4, thread 5. They can all be executing in parallel, but there's an order, which is the sequential order, if you're actually parallelizing a single-threaded program and executing them in parallel. In this case, you're taking these threads that are supposed to be sequentially ordered, or chunks of execution that are supposed to be sequentially ordered, and executing them in parallel, thread 4, thread 5, and looking at, checking if they actually have dependencies on loads and stores, if they actually violate any load-store dependencies. So every thread can do the loads speculatively. For example, assume that the loads are actually independent of any store. That could be one assumption. And keep a record that they've actually read the data. This load, for example, loads from address A and keeps a record that, oh, I read from address A. And this can be done in the L1 cache by setting a bit saying, I read the data, right? Speculatively read. And this thread 0 later on, for example, executes a store to location A. At that point, it buffers the store. And it also checks if there's a successor that has already read location A, right? If a successor did a premature read, well, in this case it did, right? This load A happened before the store A, whereas it shouldn't have happened in that order. It's because these are logically sequential threads. Just because we've executed them unsafely in parallel, this load happened before the store. So we need to detect that dependence when the store actually executes, and that's when the dependence is detected. This store basically somehow figures out that figures out a destination load happened earlier, where it shouldn't have happened until the store finished. Right? So if the successor basically did a premature read in this case, so it needs to be squashed. Right? Squashing means the thread needs to be restarted, perhaps, and maybe everything else needs to be restarted because you have now a data value dependence that was wrong, because some other thread may have read some other data value that was produced by this load later on, and it got executed with the wrong data value. Basically, you typically squash the offending thread and all of the successors when you detect such a data dependence violation, when you figure out that this thread speculatively read the wrong value. Well, you could do something smarter, but complexity increases in that case, right? You could actually figure out only those dependent instructions that have gotten the wrong value and execute it, and you could selectively re-execute those instructions that are dependent. Right? Now, this is a tough thing to do. It's very hard to figure out selectively which instructions need to be re-executed. And people have looked at this problem and they found some solutions, but in general, it's a difficult thing to do. Okay, so I've given you a lot of the concepts actually in thread level speculation. Basically, when you take a single threaded program and parallelize it unsafely, you run into these dependence issues. And the key dependence issues are register communication and memory communication, and you need to satisfy those. And memory communication needs to be satisfied dynamically, as I said over here. And this kind of communication can happen over here also, right? It doesn't need to be with the oldest thread. This is, in this case, the oldest thread and the youngest one over here. But it could happen between thread 3 and thread 4. Thread 3 can be, thread 4 can do a load A, and later thread 3 can do a store to load A, and this needs to be detected, and thread 4 and all successors need to be flushed or squashed. Okay, dependencies and versioning. Only true data dependence violations should really cause a thread squash, right? It makes sense. There are types of dependence violations. Let's say you have, in this case, I denote load A and store A. This is the later thread, let's say. The earlier thread does a load to A, later thread does a store to A. In this case, it's really a name dependence. So the hardware should really be able to handle this. Meaning there is really no dependence here. It's really an anti-dependence. It's not a true dependence, right? Basically, there's no reason for, let's say you have thread 0 and thread 1. This does a load A, and this does a store A. And this does a store earlier than this load. You should definitely ensure that this doesn't get the value coming from this store, right? And you should be able to do that by eliminating the name dependencies. And how do you eliminate the name dependencies? Well, you do a register renaming, right? In this case, these are not registers, so you can do memory renaming. Okay, and we'll see one structure that does memory renaming. Whenever you would like to eliminate not true dependencies, write after write, in this case it's a write after write dependence, right? Or write after read dependencies. Well, in this case, I guess write after read dependence, sorry. You can eliminate this dependence by renaming these locations, because essentially the store is really creating a new value which just happens to be in that location, right? A. You can actually think of the store killing the old value in that location and creating a new value, so there's no dependence really. It's really a name dependence because we didn't have enough memory locations, for example. Or you could actually create a new version of that memory location if needed. Okay, the second one is a write after write dependence. If one thread is doing a store to A and the next thread is actually doing the same store to A, the hardware again should ensure that the stores appear in order. And we've covered this subject earlier, right? If the true dependence happens when the older thread is doing a store to a memory location and when the younger thread is actually reading from that memory location with a load. In this case, if the younger thread actually read earlier than the store happened, then this true dependence needs to be detected and it needs to cause a squash because the thread that's younger read the wrong value. So name dependencies, in general, the first two dependencies can be resolved using versioning, right? Basically, every store to a memory location can create a new version, as I just described earlier, right? Because the store is really using that memory location as an address. It's really creating a new value, right? And once you have different versions, for example, whenever this store writes, it creates version 1, whereas this load is loading from version 0, right? So this load can get the correct value because it's really reading from version 0, right? At the time this thread is executing, you have version 0. When this thread is executing, it creates version 1 of that location. When this next thread is executing, let's say it does a store A, it creates a version 2, right? And this thread actually it creates all the version 1s, this thread creates version 2s. As a result, there's no, the name dependencies can be eliminated. Of course, this requires some hardware cost to tag the memory locations with the different version numbers. And one example of this is described in this paper, Speculative Versioning Cache in HPCA 1998. And I encourage you to read that paper. This is one way of handling name dependencies that are not true dependencies. Okay. The other question when you actually design speculative parallelization concepts is, where do you keep the speculative memory state? And let's take a look at that. Basically, what is speculative memory state? Whenever a thread speculatively does a store instruction, you don't know whether that store instruction should actually be committed to the architectural state, right? Because this thread may not be the oldest thread in the machine yet, in the sequential logical order, right? Which means that somehow you need to buffer that store instruction. Well, there are two approaches to this. Where do you put this store? You can put it in a separate buffer. For example, you can put it in a shared queue, store queue that is shared between threads, right? And the idea is whenever you do a store, you have a buffer, and the thread puts its version number, for example, and thread ID into this buffer, and another thread later on checks this buffer to see if there's a store to get the data from, right? If this thread is the older thread, for example, if there's a younger thread that's executing, let's say it does a load. It basically searches the store buffer to see if there are stores from an older thread to the same location, right? So this is the store buffer approach, separate store buffer approach. Now this is an additional data structure, but this is doable certainly. This is very similar to the address resolution buffer in multi-scalar processors that we will cover. Basically, address resolution buffer is a way of ensuring that store load dependencies are satisfied in multi-scalar processors. This is also similar to run-ahead cache and run-ahead execution that we have covered in 447. The basic idea over here is in run-ahead execution, you speculatively execute the program, and while you're speculatively executing the program, some store instructions actually write speculatively to memory. You don't want to expose them to the architectural state because remember, run-ahead execution is purely speculative. And the load instructions that happen in run-ahead mode get their data values from, if they're dependent on store instructions that are executed in run-ahead mode, they get their data values from this run-ahead cache. And if you're interested in this more, you can read the run-ahead papers that were assigned or that were discussed earlier. On the other hand, you can not have a separate buffer like this, but you can decide to place the speculative store blocks in the L1 cache. In this case, you can mark, basically, in the tag store, you have one additional bit saying speculative bit, right? Speculatively modified bits. And we will see this example when we talk about thread level speculation. And this speculatively modified bit basically says that this cache block was speculatively written by this thread, and normally this is not visible to the other threads, right? You need to make them non-speculative when the thread commits, and you need to invalidate them when the thread is actually squashed. Now basically what you're doing is you're really putting the store buffer into the cache and integrating with the cache. But you need to ensure that cache still operates correctly. And this modifies the cache, but maybe you don't need an extra store buffer if you actually want to keep the speculative memory state. So there are actually interesting trade-offs related to where to keep the speculative memory state, and I'd encourage you to think about it, especially when we come to multiscalar and different kind of approaches to thread level speculation. Okay, I will now delve into speculation to parallelize single-threaded programs. But before I do so, I will take a quick break, and we will get back to this very soon.